What we're going to do in this video is think about functions, not just as standalone rules, but as mathematical objects that can be combined to create entirely new functions. Just like you can perform arithmetic with numbers, you can perform four basic operations with functions: addition, subtraction, multiplication, and division. Let's say we're running an online merchandise business. The cost of the products is represented by the function f of x, while the delivery or shipping cost is represented by the function g of x. Therefore, to find the total cost, we need to add the two functions together, f of x plus g of x. This is an example of what we call the combination of functions. All right, now let's say we have two functions, f of x and g of x. We define their combinations based on their outputs at the same input value x. The sum of f of x and g of x is defined as f plus g of x equals f of x plus g of x. And the difference is defined as f minus g of x equals f of x minus g of x. The product is defined as f times g of x equals f of x times g of x. And finally, the quotient is defined as f over g of x equals f of x over g of x, where g of x is different from 0. Let's practice this together using two simple functions, where f of x is 2x plus 1 and g of x is x squared minus 4. First, let's find the sum, which is f plus g of x. To find the sum, we just add the rules together, which is 2x plus 1 plus x squared minus 4. When we simplify that, we get x squared plus 2x minus 3. Graphically, the two functions are illustrated here. F of x is a linear function, graphed here as shown, and g of x is a quadratic graph as shown. Now let's see the graph of their sums, which is also a parabola because the resulting function is also a quadratic. Next is the difference, which is f minus g of x. I encourage you to pause the video now and try this one, but be very careful with your parentheses. All right, let's see how you did. We have 2x plus 1 minus x squared minus 4. This example should serve as a reminder to distribute that negative sign across the entire second function. This gives us 2x plus 1 minus x squared plus 4, which can be simplified to negative x squared plus 2x plus 5. Failing to distribute that negative is a very common mistake, so you should give ample attention to it. Graphically, the difference graph is here as shown. As we can see, the parabola becomes downward opening due to the sign of the leading term coefficient, which is minus 1. For the product, f times gx, we multiply 2x plus 1 by x squared minus 4, resulting 2x cubed plus x squared minus 8x minus 4. And for the quotient, f over gx, we simply set up the fraction 2x plus 1 over x squared minus 4. For the product and quotient function, we got different form of functions, which are cubic and rational functions, respectively. We'll see how to graph such functions in the coming video, so don't worry about them. What we need to note here is that just like a basic arithmetic operation, addition and multiplication of functions are commutative, but subtraction and division are not. To reinforce this, let's evaluate our sum function at x equals 3. We already found the rule for the sum is x squared plus 2x minus 3. So we plug in 3 for x and solve the function, which results 3 squared plus 2 times 3 minus 3, which is 9 plus 6 minus 3, which is 12. You'd get the same result if you evaluated f of 3 and g of 3 separately and then added them. Let's check. F of 3 is the value of f of x when x is 3. Therefore, we substitute 3 into x. When we do, we get 2 times 3 plus 1, which results 7. And when we solve g of x for when x is 3, we get 3 squared minus 4, which is 9 minus 4, resulting 5. So now that we get both f of 3 and g of 3, we go ahead and add them, which is 7 plus 5, resulting 12, which is similar with f plus g of x. Hence, f of 3 plus g of 3 is indeed equals to f plus g of x. So here we see the purpose of combination function. Instead of solving two functions with similar input values separately and joining their result as shown here, we just solve the combined function once since the input is the same. But if the x value or the input for the two functions is different, like f of 3 and g of 5 for instance, then we can't use such combination, or we have to do each function separately. Alright, now we have to talk about the domain. How do we determine the domain of a function that is found from an arithmetic operation of two or more functions? For the sum, difference, and product, the domain is generally the intersection of the domains of f and g. This means an input is only valid for the new function if it was valid for both original functions. However, for the quotient, f over g, beside the intersection of the original functions, we have one extra restriction. The input must also satisfy the requirements of g of x being different from 0. Because division by 0 is banished in our math world, any x that makes the denominator 0 must be excluded from the domain. For our example, x squared minus 4 equals 0 at x equals 2 and x equals minus 2, so those values are excluded from the domain of the quotient function. Since f of x and g of x are linear and quadratic function, their domain will be the set of all real number, which leads to the domain of their sum, difference, and product function to be the set of all real number. For the quotient function, on the other hand, we'll take the real number set and exclude the numbers that makes g of x 0, which are minus 2 and 2 as evaluated here. So the domain will be the set of all real number except minus 2 and 2, expressed in set builder and interval as shown. The range, the set of all possible output values, is a bit trickier. You can't usually find the range by just combining the ranges of the original functions. Instead, you have to analyze the resulting expression while keeping your domain restrictions in mind. For instance, if a domain restriction creates a hole or an asymptote in a rational function, that will directly impact which y values are possible outputs. Let's see another example. Here, our f of x is x squared minus 4x plus 3, and g of x is 2x plus 1 over x minus 2. Now, before we do the combination of functions, let's see the domain of both functions. The domain of a quadratic function is always the set of real number. But for the rational function, we exclude the value of x that makes the denominator 0. Here, the denominator of g of x is x minus 2, which must be different from 0. Therefore, x must not be 2, meaning the domain is all real number except 2. Or in an interval form, it is expressed as minus infinity to 2 union 2 to infinity. Now, let's proceed to finding the sum of the two functions, which is f plus g of x, which will be f of x plus g of x, which is x squared minus 4x plus 3 plus 2x plus 1 over x minus 2, simplified as shown. The domain of the sum function is, as we discussed earlier, it will be the intersection of the domain of the two original functions. Hence, the intersection of the set of real number and the set of real number except 2 will be the set of all real number except 2, or the domain of g of x. For the difference and product, we get the result as shown here, and their domain will be similar with the domain of the sum according to our discussion. Finally, when we look for the quotient function, we will divide f of x over g of x, which is x squared minus 4x plus 3 divided by 2x plus 1 over x minus 2. This can be expressed by x squared minus 4x plus 3 times x minus 2 over 2x plus 1, which is multiplying by the reciprocal. Therefore, we get x squared minus 4x plus 3 times x minus 2 over 2x plus 1. When we determine the domain of this function, similar to the other results, such as the sum, difference, and product, x equals 2 is excluded from the domain. But in addition to 2, we will exclude another number that makes g of x, or the denominator of the final function, 0. Here, g of x is 2x plus 1 over x minus 2, and it must be different from 0. which means 2x plus 1 must differ from 0, resulting x must be different from minus 1 over 2. Therefore, the domain of the quotient function will be the set of all real number except minus 1 over 2 and 2. Or in an interval form, we express it as minus infinity to minus 1 over 2, union minus 1 over 2 to 2, union 2 to infinity. You might ask why 2 is excluded from the domain for the quotient function x squared minus 4x plus 3 times x minus 2 over 2x plus 1, since when we substitute 2 into the function, we get 0 rather than undefined. This is a good question to raise here. The quotient function x squared minus 4x plus 3 times x minus 2 over 2x plus 1 is expressed in a simplified form, and excluding 2 might not make sense. But the concept of quotient function is the result of f of x over g of x, which is x squared minus 4x plus 3 over 2x plus 1 over x minus 2. Meaning x's value that makes g of x's denominator 0 will automatically make the quotient function undefined. And that number is 2, where it makes x minus 2 the denominator 0, making it undefined. Please be reminded that f over g of x is always equal to f of x over g of x, where g of x must not be 0. Hence, the quotient function can't be defined while g of x being undefined. Finally, let's see that when do we say two functions are actually equal? It's not enough for their formulas to look the same. They are equal only if they have the exact same domain and produce the same output for every input in that domain. Take f of x equals x squared minus 1 over x minus 1, and g of x equals x plus 1. If you simplify f of x by factoring, it looks like x plus 1 times x minus 1 over x minus 1. And when we cancel x minus 1 by x minus 1, we get x plus 1, which is similar to g of x. But these are not equal because f of 1 is undefined, since division by 0 makes the function undefined, while g of 1 is perfectly happy being 2. This means even though both functions have same output for the rest of the inputs, their domain is not the same. Therefore, they're not equal. In a graph, f of x would have a tiny hole at x equals 1 that g of x doesn't have, illustrated as shown here. This means we should not do mere cancellation in function operation as we do in numbers or variables. Combining functions allows us to build complex models from simple parts as long as we respect the domain rules of each piece. And we're done. Hopefully that makes some sense and helps you feel confident performing arithmetic with functions on your next assignment. If this walkthrough was helpful, hit that subscribe button to keep mastering math with us here at Rimetric Walkthrough. Thanks for watching, and see you